Thank you. Thank Carl for the introduction. So, the bugs I remember. We all have them, I think. So, I'm going to talk about a few I remember, at least, because who doesn't like to learn about other people's bugs, not your own? So, about me, I was introduced 20 years ago to C++. It was my first programming language, for some reason. I'm currently working on modeling and simulation radiation physics, and that's mostly in C++ and CUDA. And this means that performance and accuracy is both important. Accuracy is a bit more important, but who doesn't like a bit more performance? But there will be bugs. And the bugs are often hiding in plain sight because, yeah, it's hard to see them. And the bugs I'm going to talk about, I've seen or investigated during my career at different places. Some bugs are mine, most are written by others. This is so everyone can have plausible deniability, and I don't put anyone under a bus or myself under a bus. But this is important because a good culture around bugs is that you don't blame the author because otherwise people will just sweep them under the rug or be ashamed or afraid of talking about them, bringing them up. Instead, you should learn from the bugs you make and then spread the knowledge so other people can find their own bugs in a similar fashion or just learn from it. It's a hugely important thing, and it's a great culture to have around these kinds of issues. And the usual disclaimer, this is slideware. This is not the original code. All the bugs are reproduced from memory only, as they are stuck there. And please, no spoilers. It's probably easy to spot the bug now because it's slideware. So I try to remove all the crud around the bug. But you don't need to just point it out and spoil everyone else's fun here. So this is the first one. You want to process some data, but just the data where you have active indices, essentially. So what you do is you sort indices, take the unique indices, and then you just process the active indices. Straightforward, I hope. We use standard unique. And if you look at this, what does the reference say here? It has a return parameter. And what does the return parameter use? Yeah, it's the end of the actual unique elements. The vector is still has the original size. So what does that mean? We have a lot of unknown data in the end of the vector. But we have notes here that it's not undefined behavior, but it's unspecified values. So that means that it's not undefined behavior to look at it, which is good, because otherwise, who knows what happens. But you should use the containers erase member function to just resize the vector instead of just keeping it. So this is a bug solved. But you don't stop there. You need to think about what happened here beforehand. Did this create some bad behavior? So you do tests. Luckily, unspecified behavior is not undefined. So the implementers need to specify what the compiler does or the library does. So you can look at the library implementation and or documentation, and you can verify the impact in your use case for this bug. in this case, you can see the end of the vector is just the original vector elements, and you have the unique elements in the front. So what happened was that, yeah, we did some more calculations than we had to, because you did some calculations multiple times. So no big issue, but it's a bug. This was caught not by a user or not by a developer, it was caught by a static analyzer, which you should always use, I think, because that can spot things inconsistent with implementation details, because they know the rules, you don't know all the rules. Yes?
Isn't that marked no discard
No,
nowadays?
no, it's not.
Okay. Room for improvement.
Yeah. So you should always read the documentation, what you use, and think about what you're using. So this is a second bug. So here you're finding the intersection between a line and a surface in 2 dimensions. So what you do is you step backwards, and what you want is to be inside in the end. And if you miss the geometry, you will return false. So what you do is you step backwards and you take small steps forward until you hit you're inside, and then you return, and you're done. Otherwise, you return false if you step too many steps. But if you want to improve the accuracy of this algorithm, you can reduce the step size. But what happens then? This is the green line. You step one step, and then you just go straight down. What happens here when you have a small step? So if you have a very shallow angle towards the geometry, so a small component in x, the position plus the increment will just be the original position. So you don't advance in that direction, you just advance in the other direction. And you actually miss the geometry, even if you should hit it. So your more accurate algorithm does actually the wrong thing. And this trying to drive home the fact that you shouldn't trust floating point numbers do what you think they do. They are not real numbers. They are floating point numbers. So this expression here does not add up in floating points. So you should always be careful when adding number of different sizes, and you should think about what rounding does for small numbers in expressions. So think about what happens if x is small or y is small compared to 1, because that will have a hugely important thing. And also test with extreme values. Test with 0.000001 or a huge number to catch these things and make sure that it does what you think they do. Next bug, bug 3. So this is 2 kernels in a parallel GPU world. So what they are executed in parallel. So each kernel get a unique indices, and then you add the numbers b to the numbers in A and return A. It's a low-level code, and both A and B are n-sized. So this works pretty good. So you have an add kernel and a subkernel, so you can add and subtract numbers in arrays. But if you want to do this faster, you should use fewer threads. So each thread does more work. So you have fewer threads but they advance. Yeah, this is the wrong. I see now. But they advance by the number of threads you use, so not by index here. And this was a lot faster, you can say. So then I thought I'd do the same for the subkernel. Same implementation, but it was wrong. And now I see I've written it wrong also, but yeah. So it's a lot of bugs, but essentially, what does that trailing semicolon do?
Advertisement for Clang format.
Yeah, I guess. But it's legal code, but we'll just do a loop incrementing the indices and then add the last indices. Very fun. The fun thing was that I copied that line to all the kernels I use because so I kept finding semicolons in for loops for a while.
But it was very fast.
Yes, it was very fast. So I was sad that it went a bit slower when I fixed all the bugs.
Yeah.
Wouldn't the compiler remove that for loop?
No. It will increase the I.
Yeah, but
But it will be optimized.
I is not used.
Yeah, this is. I see that.
Okay.
Index should be I there
Okay.
always.
Okay. Yeah. Then it wouldn't be used.
So that's one semicolon, and it's also the fact that you are programmed almost to just write a semicolon at the end of each line you write. So semicolon enter, semicolon enter, semicolon enter. So it happens. So next bug. So I want to sample a random distribution of numbers in normalized here. So this is the code to do that. So you sample x, you sample y, you transform it so it becomes normally distributed numbers in 2 dimensions. And then you add a random number to an image, and you get this image. And you do some other things with that. But you see there, z is also used, but it isn't used. So it's an old value. But so if you remove it, you end up with this. Yeah. I just want to point out that random number generators are really hard to test. This is not the original random number generated in the bug, because I don't have the hardware used for that. So I chose another vendor's random number generator, and sure, it's nowadays a smaller vendor, but it was the biggest vendor of computer equipment back in the day. So that random number generator shown here was used at least everywhere. But our vendor had a correlation between the threads, so the random numbers wasn't random in regards to each other. So in this case, this random number generator, the 3 numbers are correlated to each other. So if you sample 3 numbers, they will show a pattern. So they won't be a complete random independent numbers. Just make sure you use a good random number generator. I'm going to hold a next talk about random number generators, so prepare for that. And the last bug number 5. So this is a bit of code. It does accumulation of all the columns in a matrix in parallel. So I have a parallel instantiation that runs a small for loop, and you have a buffer there to keep the threads from trampling on each other. But when you swap computers, it runs 10 times slower. And then you look at the computers and see what the processor they have. So you went from a 10-core processor to a... Oh, okay, there we go. You went from a... Yeah, I spoil you, sorry. You went from a 10-core to a 28-core processor. And it's much faster, but it's 10 times slower. And why is that? Yep.
Cost sharing?
Nope.
No.
You create a buffer there per core or per thread. So what does each thread has as its own cache? So if you're running 50 threads and you have 38 megabytes of cache, you have less cache per thread. So in this case, it was half the cache per thread. So in the end, you will get cache eviction. So it will have to reload from RAM, the buffer, all the time. And it's a subtle error because, yeah, all the numbers are bigger on the new computer, but it's not when you think about it.
It's not really a bug.
Performance issue.
It's a performance issue, sure, but it's a bug in the sense that your implementation is worse for a better computer. And if you get complaints, yeah, they will say it's a bug. So in conclusion, test your code, test others' code, use all the tools you can find to make sure you don't have any bugs, and stressing on, have a good culture around bugs, admit and learn from your failures. And that's it. Thank you. Any questions or comments?
I think it's really great is being open with that. You make mistakes, and what can we do to prevent them?
Yep.
I really like your message.
Mm-hmm. Yep.
In the kernel example,
Yep.
if you kept your variable inside of the loop, it would have caught it, right?
Yes.
So
But this is a C way of doing things. You can't instantiate the variable in the for loop in C.
Also always use curly braces.
It doesn't matter. If you have the curly braces on the new line, it doesn't matter because it's just a new scope. Then the indentation will always, anyways. Yeah.
That's why we should have the curly brace on the same line. So
Yeah, that's. but we don't want to start a fight here.
But if I keep the curly braces on the same line, my KPI goes down, which makes less money. So I have to keep them on separate lines.
Can you repeat it? What did you say?
I say if you keep the curly braces on the same line,
Yeah.
my KPI go down, which means I get less money. It's not really.
I have the feeling we reached already topics for the break.
I actually want to say one other thing about this with performance things, because it also, like, when you find the bug, it doesn't feel like a bug, but you know it's because you have, in this case it was different machines, but I have also that you kind of fill the cache or whatever, the pipeline or whatever, which means that all of a sudden it works for a long time, and then all of a sudden you just come to this point where you overflow, and you don't know. It doesn't look at the code. It's not a bug or anything. But you don't handle this when the computer is too slow or if there's something else on the machine or something. So there's many things that don't look like bugs, but you really need to handle anyway.
In the previous example were floating point problems. What was the fix?
What the fix is, you accumulate the step size instead of accumulating the position. So you increase the total stepped instead of just moving the position. And then when you exit the loop, you add the total step to the position.
Or use stood lerp. Right?
Depends. If you use it correctly.
Yeah.
Okay. Yep.
How did you solve the cache issue with the cores? Because it seems like it depends, like the math to figure out what's the optimal number of like cores you can throw at the problem, depending on how fast you can fill the cache and how fast you need to evict it.
Yeah. What was done is that you essentially do the parallelization in the other direction. So you parallelize over the rows and not over the columns. Because then you don't need the buffer being the whole array, a copy of the whole array. You just need a buffer that's smaller, in a smaller buffer. Because and then you just because you're not interested in caching the data, you're interested in caching the buffer. So if you know you're just accumulating all the columns, then just each thread accumulates the parts of each column in parallel. Yes. Thanks a lot for listening, and I think there's snacks now.
Yeah, thanks for this awesome.